This is the second of the video segments that I'm making for solution homework problem number 5. Here, it's the expressions are given to you, and you're asked to find a period and plot it. Okay. Obviously, the whole objective of at least this part of the book is for you not to use your calculator only if it's needed for verification or if it's absolutely necessary. So we're not going to use our calculator. Now, the function 1/2 tan of x. First of all, when it comes to this, you compare it with tan of kx, where the period is pi over k. K is 1, and so this is equal to pi. The period of this function, there's no doubt about it, is pi. And if I ignore the 1/2, tangent of x is one of those graphs that we did in class, and you're supposed to at least be able to do it quickly. Okay, so we're going to plot this thing between minus pi over 2 and pi over 2. Just for the heck of it. I mean, there's no reason why you should stick to this interval. However, in the book, when it came to tangent, they, for certain cosmetic reasons, they do it between minus pi over 2 and pi over 2. Okay? Now, also notice that when you look at tangent, remember tangent, never mind about the 1/2. This 1/2, all it does is a compression or a stretching, in this case compression, in the vertical direction. But when you look at tangent of x, it's a sine of x over cosine of x, right? So the places where this denominator are 0, we have a problem. And that's exactly at pi over 2 and minus pi over 2. Within this interval, they're like that, okay? So when you look at tangent of x, in the book, the graph is drawn like this, okay? For example, when x is pi over 4, this height, tangent, is 1. And when x is minus pi over 4, this height is minus 1. Okay, fine. This height is minus 1. This height is minus 1. Now, because we have 1/2 here, the entire thing is shrunk in the vertical direction by a factor of 1/2, or yeah. So this point 1 is going to go to 1/2. This point going to go there. So the graph is going to look like so this height of 1 is going to go to a height of 1/2. This height of minus 1 is going to go to a factor of minus 1/2. The graph of 1/2 tangent of x is this red one. Based on the knowledge of tangent of x, we are able to draw 1/2 of tangent of x, which is that red curve. All right. Now let's go and do this. Very similar. So let me bring it up. Okay. So let's do problem number 14. Y equal to 2 cotangent of x. And again, the period is here, k is 1. K is 1. The period is pi over k, which is once again pi. Now, I want to tell you that in the book, I want to remind you that, as I said, for cosmetic reason, cotangent, when it comes to one period, is drawn between 0 and pi. Whereas tangent, minus pi over 2 to pi over. There is no reason, there is no other reason aside from, very superficial reasons that exist. Okay, so we're going to draw cotangent between 0 and pi. I want to remind you that we drew tangent between minus pi over 2 and pi over 2, which really doesn't matter. They both have the same period. Now, we concentrate on cotangent, and let me remind you that this was cosine of x over sine of x. Okay, so the function blows up where sine of x is 0. That means it's going to blow up right there at pi, and it's going to blow up. It's going to blow up at pi, and it's going to blow up at 0. Okay, when we take an intermediate point, for example, pi over 2, and we plug it in that expression, either in your calculator or just in the expression for cosine of pi over 2, sine of pi over 2, we get a 0. And when we take another point, let's hypothetically say, oh, I don't know, maybe pi over 4, and we plug it in this expression, you get cotangent is equal to 1. So the value of the cotangent is positive at pi over 4, and it's going to blow up here. So let's put this information together. And there we are. This is the graph, and this height, by the way, is 1. If this was 3 pi over 4, this height is minus 1. Okay? Now we have a 2 there. That means you stretch everything by a factor of 2. So, for example, this point which had a height 1 is going to go to height 2. This height which had a height 0 stays there. And this height which was minus 1 goes to minus 2. So can you visualize this? The function goes to infinity, goes to 0, goes to minus 2, and then goes to infinity. So that red one is the graph of number 14. I urge you to go ahead and put these things in your calculator and select your, the x range so that don't go from minus 100 to 100 and things like that. So we know what the period is. So you should be getting these graphs. Let's go to number 16, which is cosecant. If we know the graph of cosecant, the 1/2, all it does is shrink it in the vertical direction. So let's do another practice. We have done this thing in class several times. We're going to do it again. Okay, so we have this guy. Now, as I said, if you ignore the 1/2, just concentrate on cosecant. Remember, cosecant is 1 over sine of x, and it helps me. It always helps me because it tells me what are the trouble point of sine. The period of cosecant is 2 pi. The period of cosecant, secant, sine, cosine is always 2 pi over k, and in this case, k is 1, so it's 2 pi. So we can plot this thing between anywhere we want. We can do it between 0 and 2 pi. We can do it between minus pi and pi. In the book, when they talk about cosecant, they're drawing it between 0 and 2 pi. Again, that's not necessary. You can do it in any interval that is of length 2 pi. For example, minus pi to pi. Now, let's see now. Why they would do it like this? Because they show you immediately what the trouble points are. For example, when x is 2 pi, you have a problem. The function blows up. When the function is 0, the function blows up, because sine is 0. And when the x is pi, the function blows up. Okay? All right. Now, let's look at a few more points. This is actually a very useful device. I'm going to draw it just like I did in class, and then I'm going to delete it. Let me draw, because this is sine of x, let me draw sine of x for you. Sine of x looks like this, right? So at this point, sine of x is 1, and 1 over 1 is 1. So the graph of cosecant, which is 1 over sine of x, is going to look like this. This is how it can be argued, because look, I'm going to erase the sign now, and it makes sense because the height of sine is 1 here. 1 over sine is also 1, and the function blows up at these two ends. And the same thing down here at this point, which is incidentally 3 pi. What is that? Let me see. This point is pi. See now, this is pi plus pi over 2. 3 pi over 2. This is the point 3 pi over 2. The value of sine is minus 1. 1 over sine is also minus 1. And then the function 1 over sine x blows up at these two endpoints. Now, this is the graph of that function without the 1/2. If you have 1/2, this red one is cosecant of x. Let me draw the blue one for you. The blue one is 1/2 of cosecant of x. So every height, this whole thing is shrunk by a factor of 2. So this height was 1, it goes to 1/2. Everything else is the same. So this blue one is 1/2 of cosecant. And this height was minus 1, it becomes minus 1/2 right there. So that blue one is 1/2 of cosecant of x. Okay, let's go to number 23. I'll close this, open it up again. This is what we're interested in. I'll write it here. Cotangent of x plus pi over 4. If we did not have this plus pi over 4 and we only had cotangent of x, it was done in class, it's in the book, and you did it earlier today in video segment 1. All this thing does is shifts it to the left by pi over 4. Now, I told you that in the book, now keep in mind that the period of cotangent of x is pi, okay? And you can draw it in any interval, which is of length pi. You can go from minus pi over 2 to pi over 2. But in the book, they go between 0 and pi for cotangent. That's how they decided to do it. And cotangent, okay? So if you look at cotangent of x, it blows up at these two endpoints. When it's pi over 2, the height is 0, because remember, cotangent is nothing but cosecant of x over sine of x. When you use pi over 2, cosine is 0, sine is 1, so the function goes through here. And if you pick another value, for example, just hypothetically pi over 4, cotangent has a value 1, so does tangent, of course. Therefore, it's a positive value. So it goes like this. This is the graph of cotangent. And this height, incidentally, is 1. At pi over 4, we have height 1. Now, we have a shift. We have to have a shift to the left of magnitude pi over 4. So everything is shifted to the left by pi over 4, okay? For example, this vertical asymptote goes here. This vertical asymptote goes there. Okay? And the graph is going to go, this whole thing is shifted to the left by pi over 4. And now let me see, where does that go? That goes to 0. So the graph is going to look like this. This red one is exactly what the graph is. The distance between any two of these, horizontal distance, should be, oh sorry, this point goes through there. That's a mistake. Let me clean this up. The horizontal distance between any two of these must be pi over 4. Let me erase this. Okay, very good. Let's try it again. Everything, this length, the length that you see here, from here to there, it's pi over 4. Okay? So that point goes here. Okay? This one goes there. So the curve comes down. It passes through this point. Okay? And it goes down here. and it goes down like that. So the horizontal distance between any 2 points on the graph is the amount pi over 4, which is this much basically. Yeah. Yeah. All right, let's go and do that fellow. Okay. I'm just hoping that this was, yeah. I could have done a better job on this because somehow for this was not quite drawn to scale. But that's okay. Let's move on to the next problem. Let's do this one. 2 tangent 3 pi x. So let me close this, open it up again. Which problem are we doing now? We are doing that problem. Okay. So y equal to 1/2 secant of x minus pi over 6. Okay. So first of all, uh, if you temporarily ignore this 1/2, all that does is shrinking or stretching in the vertical direction. In this case, shrinking, of course. If you look at what I've got here, k is 1. That means the period is 2 pi. 2 pi. It's always 2 pi over k for secant is 2 pi. And this is a shift of pi over 6 to the left. Okay, so if we know how to graph secant of x, we are in business because then we shift it to the left by pi, to the right by pi over 6 because this is minus the positive number. Shift it to the right pi over 6 and then shrink the graph in the vertical direction by a factor of 1/2. So let's go ahead and let us remind ourselves how secant was done in the class in the book. Okay, secant, if you look at it, it was plotted between 0 and 2 pi. So there we are. Let me actually make this thing 2 pi. Okay, this is 2 pi. All right. And remember, secant was 1 over cosine. So the trouble points for secant are places where cosine are 0. So this is the point 1, no problem. At pi over 2 and 3 pi over 2, we got problem with secant because in those places cosine is 0. So this is pi over 2. This is 3 pi over 2. We got trouble. Okay. Now let's see now. Again, we're interested in 1 over cosine. So what happens at pi? When x is pi, cosine of pi is -1. So 1 over cosine of pi is going to be also -1. So the curve goes from here. So obviously the graph of cosine, 1 over cosine or secant goes like that. And you can check this thing against the stuff that we have done in the class and in the book, like that and like so. So this height is 1, this height is -1. What you see there is the graph of secant of x. Now, I'm going to shift this thing to the right by pi over 6. Now, it's going to have to be careful. This red one, pi over 6, let's be careful here. This distance is pi over 2, right? So if I want to shift everything by pi over 6, pi over 6 is probably that much, okay? This is pi over 2, pi over 6 is probably that much. So every point moves to the right by the amount which I've given you by that much. So this vertical line, if I pretend that distance is pi over 6, is going to go here. This vertical line is going to go there. Okay. This graph is going to go like that. This graph is going to go like this. And this black one is going to go like so. You see, the distance between the black curve and the red curve is supposed to be pi over 6. Black curve and the red curve, okay? The distance between them. So these distances pi over 6, okay? Now, the only thing is that we have a factor of 1/2, so everything is reduced by, for that red curve is reduced by a factor of 1/2. So the height that was 1 here is going to start here at 1/2, and it's going to go up. I'm going to try to squeeze it there. And this one is going to come down here, and it's going to go up, and it's going to get squished between the asymptote and the red curve. And finally over here, a factor of 1/2 is over there, so it goes to 1/2, and then it gets going to get squished between the red curve and these vertical asymptotes. Look, the reason that we are doing these things manually is for you to develop a feeling for these, and you keep doing it repeatedly so that you don't treat these as complicated. It's just that, remember, the harder these graph gets, the harder meaning that the more involved they get, you're going to have to be very careful in drawing it to scale and things like that. But I think you're developing good feeling for what these things are. So I'm going to stop this video segment at problem number 35 because I don't want these to get too long. Then I'm going to come back and do these four in the video segment 3.